question 2 for chapter 5, and it asks, consider the reaction of 2-chloro-2-methylpentane with sodium iodide. Assuming no other changes, how would it affect the rate if one simultaneously doubled the concentration of 2-chloro-2-methylpentane and sodium iodide? Now let's just look at the equation given below that has like the 2-chloro-2-methylpentane and the sodium iodide. Now we can see that the iodide and the chlorine, they switch places, so it seems like a substitution reaction because nothing was eliminated. So we can like scratch off E1 and E2 reactions from occurring. Now let's see this. We know that sodium is usually a spectator ion in most cases. In this case it definitely is, so we can just ignore the sodium, and all we're left with is iodine. Now iodine is a strong nucleophile but a really weak base, so that's what SN1 and SN2 reactions require, a strong nucleophile. Now the way we determine if it's an SN1 or SN2 reaction that is favored is we have to look at the carbon that's connected to the leaving group, which is right here. This carbon here is a tertiary carbon, meaning that it's too sterically hindered for an SN2 reaction to occur. SN2 reactions can only happen on a primary and a secondary carbon. They cannot happen in a tertiary carbon. SN1 reactions happen for tertiary. So now we know that this will be an SN1 reaction. Now, if you remember, the rate order of an SN1 reaction is the substrate to the power of 1, but the concentration of the substrate to the power of 1, but the concentration of the base does not affect it. So we care about the 2-chloro-2-methylpentane, but we don't care about the concentration of sodium iodide, except that it cannot be the limiting reactant. So we definitely have enough sodium iodide because they both have the same amount, but its concentration won't affect it other than helping it proceed. Now, the word problem said that the concentration of our substrate, which is 2-chloro-2-methylpentane, it was doubled. And 2 to the power of 1 is 2. And the weak base, which is sodium iodide, it was also doubled, but 2 to the power of 0 is 1. So the way the rate order work is you multiply the concentrations, which in this case is 2. Now that's why B is the answer. They double in rate. Now it can't be A because, well, the A was increased, and it can't be C or D because it was increased by 2, not by 4 or 3. The second question I have is predicting the major product of this reaction. Now looking here, again we treat sodium as if it's a spectator ion. We have methyl oxide. Oh, I already have it drawn there. This is a really strong base and a strong nucleophile, and it's dissolved in alcohol. Now because it's a strong base and a strong nucleophile, it'll be performing a beta elimination, which requires removing the leaving group and also taking one of the hydrogens connected to the beta carbons with respect to the leaving group. So it'll either pull off a hydrogen from this side or from this side. But because this side is more stable, because it's more substituted, the this will be gone, and it'll also pull off a hydrogen from here as well. So now a bond will be formed between the alpha carbon and the beta carbon here. Looking here, we can see that D and C aren't the answers because they don't have that. But now let's look at A and B. They both have an alkene in between the alpha and the beta carbon. And if you read it, they're both the same product, but they're drawn differently. Now, my guess, because I've been trying to figure this one out, but it's been tough. I'm thinking that the reason why it rearranges, because I checked in B, is not the answer. The reason why it rearranges to form A is because, again, it is dissolved in alcohol, so it could be that the alcohol had affected it earlier and it caused a methyl shift to occur. Or it'll be more stable this way because it's closer to a cyclopentane, and if this last one shifted, it could be a cyclohexane. So I'm thinking that's why it shifted into that and why B is not the answer.